Hello, everybody. I'm Jesse Jenkins. I'm a new assistant professor in the Department of Mechanical and Aerospace Engineering in the Andlinger Center for Energy and Environment. And this is my first course at Princeton, so I'm delighted to see all of you here and excited about the attendance. I had no idea how many folks would register, so it's great to see a full house. In fact, if this gets too crowded, we might have to find a bigger room, something we certainly can do. So this course is an introduction to the electricity sector, and it covers the topic from three different interlinking perspectives, which I'll explain in this introductory lecture. From an engineering perspective, an economic perspective, and a regulatory perspective. I offered the course with that sort of interlinking, interdisciplinary perspective because after working in the electricity sector, both as a professional and as an academic for about 15 years, I found that without an understanding of all three of those topic areas, it's very difficult to do work effectively in the electricity sector. Whether that's conducting academic research, starting a company and figuring out your business model, developing in technology as an engineer or technologist that has to fit into this system. You can tackle that primarily as an engineer or primarily as an economist or primarily as a business person or primarily as a policy or regulator. But without a full understanding of the interlinking components, you'll run into some problems and you'll probably make some mistakes. So the idea of this course is to provide everyone with a foundation to conduct further work in the electricity sector that draws on all three of those concepts or those topic areas. It's going to be fairly broad, and so we're going to move through a lot of topics quickly. Some of them, like thermodynamics or power generation, or how solar cells work, we have entire courses here at Princeton to go in depth in a full semester. So we're clearly not going to cover that level of detail, right? We're going to cover it for one lecture and then move on to the next topic. But hopefully that's going to provide you with at least an introduction to the concepts that you need to know. Some of you, it's a diverse class with a lot of different backgrounds. We have both undergraduates and graduates that are meeting in the same course for lectures. And some of you are engineers, some of you are in social science, some of you are in liberal arts, some of you don't know yet. So there's going to be a pretty broad background, and the goal of the course is to teach to where everybody's at. And so my only caution is for some of you who have already taken a thermodynamics course, you will find the lecture on thermodynamics to be a review, and you might sleep through it. But I guarantee you there are topics that you are not going to be familiar with in the rest of the course, right? Because probably you haven't taken a master class on economics or regulation as well. For those of you who are coming from the Wilson School, from the economics department, you're going to be familiar with the microeconomics concepts, but hopefully you'll learn something new in the economics section. And I think for most of you, unless maybe you're a graduate student that focuses on institutional design and regulation, the entire second half of the course on regulation of the electricity sector will be new to all of you. So that's sort of the goal, okay? So the lecture for today is going to cover why we focus on electricity, so the role of electricity in society, why it's such an important topic to study and understand, its role in human development and economic activity, why, for me, my sort of main motivation to work on the electricity sector is its role in driving climate change and in delivering solutions to climate change. Talk a bit about the changes in the distributed energy resources and the decentralization of the grid are currently bringing to multiple locations that drive a lot of interesting questions in research and engineering as well. And then we'll talk about why regulation. Why do we spend about half of this course focused on regulation? Then I'll talk about the course structure and the kinds of assignments that you're going to face throughout the class. Okay. Any questions before I dive in? You're all in the right place, right? Okay, good. So why electricity? I spend most of my time thinking about electricity. I'm an energy systems engineer, and I work at sort of macro regional scales. And I don't only focus on electricity, but it's the primary focus of my research and my activity. So I wanted to spend a little bit of time talking about why, because I think it also motivates why this course is important and worth spending your time on. So first of all, from an engineering perspective, it's worth recognizing that you can consider electric power systems to be the largest interconnected machines that humans have ever built. Why do I say an interconnected machine, right? You think about a laptop as a distinct device, or you go to your thermostat and you turn it up or down. You think about that just as a single device. But the reality is that that device, anything that consumes electricity, is connected to a synchronized electricity grid, such that whenever you change your consumption up and down, flip on a light switch or turn it off, turn up or down your air conditioning or your thermostat for your heater, that's connected to a continent-spanning engineered system that is perfectly synchronized, not at a minute-by-minute basis or a second-by-second basis, but 1/60th of a second. Every 60 hertz, that system is synchronized within a very tight tolerance, which means that when you turn your thermostat up, somewhere out there in the grid, a gas turbine or a hydro turbine or a wind farm speeds up a little bit. And when you turn it off, it slows down a little bit. And we're trying to keep all of that in sync such that every generator that's connected to this system, and every electric motor that's connected to that system, whether it's in a fan or the fan that's powering this, that's cooling off this projector, they're all moving in phase, so that they're all exactly lined up within a very, very narrow tolerance of the same 60 hertz rotating frequency. I find that personally pretty amazing because these are not small systems. They span continents. This is a map of the Eastern Interconnection, which is one of the 4 principal grids in North America, which spans the entire area that we show here, except for Hydro-Quebec, that portion up there in the corner. It's got its own system. And so that anywhere in this system is really one interconnected machine. Any electrical device that's connected anywhere across, everywhere from Kansas to the tip of Florida to New Brunswick, is all part of the same interconnected machine. So from an engineering perspective, this is an enormous feat of engineering, and it makes the physical tolerances of this system extremely important to understand, because everything here is working at the speed of electrons, right? It's moving at the speed of electricity, and that's extremely fast. So, hard to design a car, sure, that's a challenging machine. Hard to design a rocket, sure, that's a challenging engineering problem. But we're talking about the biggest engineered machines humans have ever created that span continents. This is the Eastern Interconnect. This is a map of the Western Interconnection, which is the other large grid in the US that spans the western half of the country and most of Canada in the northwest. Texas has its own grid because Texas does everything on its own, right? And then, as I mentioned, Quebec and Labrador have their own grid. So those are 4 large interconnected sections that are each of which are distinct. So they're all synchronized within that same area. Europe also has several enormous interconnections. The whole blue area here, including parts of North Africa, is the Central European Interconnect. The islands are their own systems, and then the Nordic and Baltic states have their own interconnection as well. But these are systems that span hundreds of thousands of miles of transmission lines, millions of miles of distribution wires that come to individual homes and businesses. They have on the order of several thousand generators. There's about 9,000 individual generators of 1 megawatt or larger in the United States, all generating power within the same interconnection. Potentially millions of distributed generation devices like solar on rooftops throughout the country. And of course, hundreds of millions of consumers all going about their daily business, generally blissfully unaware of all of the amazing engineering that goes on behind the scenes to make everything work. So they also involve individual technologies that themselves are complex engineered devices, right? So the whole system is complicated, but each individual technology is an important engineered device as well. So this is a diagram of a combined cycle power plant, which is a way to efficiently generate electricity from thermal sources that involves both a combustion turbine and a steam cycle. So we take the heat coming out of the combustion turbine and use that to generate additional steam to run a secondary power generation cycle. Why it's called combined. It combines both the Brayton cycle of the combustion turbine and the Rankine cycle of the steam turbine to generate efficiency, to generate electricity at a high efficiency, right? And we have hundreds of thousands of these generators, or thousands of these generators throughout the country, all running different types of systems that we'll learn about, different types of power generation cycles. We have new devices like lithium-ion batteries, solar cells, wind turbines, all contributing to these as well, each with their own interesting engineering challenges. Don't take my word for it that this is an interesting engineering topic. The National Academies of Engineering put out a report maybe about a decade ago now on the greatest engineering achievements of the 20th century. Right? So they looked back at the previous century and figured out what were the most important societally impactful engineering decisions. And the number 1 on that list was electricity. But it wasn't just number 1. If you go down the list of the top 20, I bolded all the other ones that fundamentally rely on electricity as well. Right? So take away this system, and you can think about all the things that you count on in your day-to-day life that power modern society that would vanish. Right? Whether that's water supply and distribution that relies on electric pumps to drive irrigation and pumping and distribution transportation, electronics, radios, computers, air conditioning, the internet, even many health technologies, refrigeration of vaccines, et cetera, all fundamentally rely on electricity. This is a graphic of the total flow of both energy in the US economy. It's called the Sankey diagram or doodle charts, right? And so on this side, we have all the primary sources of energy, the inputs from fuels and biomass and wind and solar and other renewables. And those flows then move into various intermediate forms where they're converted in the top to electricity and then consumed in different types of end-use activities, residential, commercial, industrial, transportation, et cetera. And what we can see if we zoom in is that electricity consumes about 38% or 2/5 of all primary energy that we produce in the country goes into the electricity generation. That includes about 35% of all the natural gas in the country and 90% of the coal. So most of our coal goes into electricity production. That electricity then goes on to supply about 1/5 of all of our final energy consumption activities, including about half of our residential and commercial energy consumption and about 10% of industrial activity. So huge amount of electricity consumed across the economy. That also makes it about 2% of US GDP that we spend every year on electricity bills. We spend about $400 billion in the US every year on electricity. And that's, I raised that number because it means that even a 1% improvement in how efficient we produce electricity or distribute electricity or regulate utilities so that they're more cost efficient can save $4 billion a year. These are not small amounts of money that are at stake. These are big, big sums. They represent a substantial share of GDP. So do something wrong and make electricity twice as expensive, that has an impact. Do something smart and to make electricity more efficient and cheaper, that has a huge impact as well. Electricity, of course, is also central to human development. No wonder, given all of the important achievements of the 20th century that are powered fundamentally by electricity. So this graph here shows GDP or GNI, gross national product per capita, as a function of electricity use, right? And you can see it's not quite a perfect linear correlation, but almost, right? So the more developed a country is, the more wealthy its population is per capita, the more electricity you consume. There's some variation based on geography and development patterns, et cetera, but the correlation is extremely strong. And if you run this, if you go to Gapminder or Google's data viewer and you play this over time, you can sort of see, oh, this is true over time for individual countries as well. That as they develop, they consume more and more electricity to power modern activity, right? And so if we're thinking about China here and how we can bring, how China brought 1 billion people out of poverty over the last 2 decades, it's a story of increasing electricity consumption, among other things, one of the primary interests. And if you're thinking about countries down here that have a long way to go to reach modern living standards, finding cost-effective and reliable ways to supply electricity to power, not just day-to-day activities like lighting and cooking, but industrial activities that power economic development is central to the story. I bring up the latter because there's still nearly 1 billion people globally that have no access to electricity, and many, many billion more who have inadequate access to electricity. So this is a progress report tracking the Sustainable Development Goals that the United Nations set around the millennium. SDG 7, so the seventh development goal, was to ensure universal access to electricity and clean cooking fuel. You can see that we've made progress over the last decade or so. It's down by about 400 million people from 2010 to 2017 that have no access to electricity. But we've made very little progress in access to clean cooking fuel. So there's still nearly 3 billion people that rely on primitive sources of fuel, solid biomass or dung, or wood, et cetera, coal, to provide their cooking fuels, which is one of the leading interior air pollution from dirty cooking fuels is one of the leading preventable causes of death worldwide. Over 2 million people die annually due to air pollution issues. Yeah. No, I think they count propane and kerosene as clean cooking fuels. So they're fossil-based, but they're much cleaner air pollution for interior air pollution than reliance on solid biomass, which is that number. Yeah. So this doesn't even mean you have a clean natural gas burner or you have electric boilers or burners. You could be burning kerosene, which is quite expensive and has its own smaller but important air pollution, interior air pollution. Yeah. This is a map of Africa at night. I raise this because there's, we focus a lot on China and India, but there's over 1 billion people that live in Africa as well. And if they follow the same kind of development trajectory as we've seen elsewhere in the world, and they should, then this is what we might see from space in 20 years. Right? So we got to light an entire continent full of people. And this challenge is enormous. The institutional challenges that are involved, the engineering challenge, the planning challenge, and the environmental impact of all of this, all of that intersects in important ways. And so we're going to try to understand some of the key concepts from each of those domains that might be applied to this particular challenge, among others. So then comes climate and decarbonization. So the electricity sector is an integral part of both the causes of climate change and an even more important part, I'll argue, of its solutions. We take sort of a high-level step. The challenge, of course, of climate change is driven by cumulative emissions of greenhouse gases, and particularly carbon dioxide, and their accumulation in the atmosphere, where they have a warming impact on the overall climate. If you break it down simply, this is the Kaya identity, named for Yoichi Kaya, who coined it in the 90s. Just sort of a development of you might have seen the IPAT formula for any sort of environmental impact, which is impact is a function of the population times the intensity of that activity times the environmental impact of the technology, so IPAT. This is a development of that, which tells us very simply that carbon dioxide emissions are a straightforward function of the total population. The economic activity per capita, you can use GDP as a measure or any other unit of economic activity or social welfare. The energy use required to support at each unit of economic activity, so energy per GDP, and the amount of carbon required, the carbon emissions required to support each unit of energy production. So population times wealth per capita or economic activity per capita times energy per GDP or energy intensity times carbon intensity of our energy supply. Okay, and if you multiply all the terms, everything cancels down to CO2, right? So it's an identity, fundamental relationship. So obviously the population's going up, and we have very little direct influence over that. The most important things we can do are to foster economic development, education, and empowerment of women are the most important levers to reduce population growth historically. And we may be on track to see a peak in global population sometime this century, but at much higher levels than today. We're at about 7 billion globally now. We should probably be planning on a world of 9 or 10 billion before we reach that demographic peak. At the same time, of course, we want GDP per capita to increase substantially. Even if you're in favor, you think we're sort of overly wealthy in the wealthy parts of the world and want to redistribute wealth more evenly, that's not enough to bring up the poorer portions of the world to at least a modest living standard that we might aspire to. And if we think about redistribution as being quite difficult in practice, to say the least, we should be planning for a substantial increase in GDP going forward, right? So if the first two terms of this equation are going up, and we have moral and economic reasons to think that they should, that leaves us only with the final two terms to try to mitigate climate change, right? We want to counteract that. So if we want CO2 emissions to go down, the energy intensity of economic activity and the carbon intensity of our energy supply have to go down faster than population growth and economic activity are going up. And it's not just that they have to decline somewhat or even stabilize. They have to drop. We have to drive total global greenhouse gas emissions, particularly carbon dioxide, to zero as quickly as possible. Climate change is driven by the total stock of CO2 in the atmosphere, not by the annual flow or emissions rate, right? And so that means that if we want that stock to stabilize, we have to bring down the rate of human-caused emissions to be equal to the rate at which the natural carbon cycle removes CO2 and other greenhouse gases from the atmosphere and sequesters them in other sources. And since it's unlikely that we're going to entirely eliminate some of the non-CO2 greenhouse gases like methane from agriculture, from rice paddies, from livestock, et cetera, or nitrous oxides from fertilizers, that really means we have to get carbon dioxide emissions levels down to zero and then even negative. So this graphic is from the recent IPCC special report, the Intergovernmental Panel on Climate Change, special report on what it would take to keep average global warming to 1.5 degrees Celsius. We're already at about 1 degree. You can already see the impacts of that all around us. And what they showed is several illustrative pathways for global emissions to try to stay below that 1.5 degrees Celsius with a reasonable chance of success. And if you kind of condense down to the core range, the window for that is to basically bring global emissions down to net zero and then negative for carbon dioxide by sometime between 2045 and 2060, roughly mid-century. That requires really an unprecedented change, right? So you can see that, we're on a slight increase still globally in emissions. We haven't even turned the corner in terms of driving global emissions down. And then basically immediately after now, in 2020 is right at the peak of that, we need to start driving emissions down at 6-7% per year. Okay. That's probably not going to happen, right? You don't turn the global economy on a dime like that. And so the reality is we're going to have probably a slower curve despite our best efforts. And that might mean that we hit net zero emissions sometime in the 2 degrees Celsius window, sometime between 2060 and 2080, if we're aggressive. And later than that, if we fail in enacting appropriate policies to drive this transition. Okay. Is there a hand? Okay. So this is the challenge overall globally, and for developed countries in particular, like the wealthy United States or Europe, we have to lead this transition, right? We can't just achieve the average rate. We should be leading because other countries that are still in an earlier stage of economic development are likely to see an increase in absolute emissions going forward, at least for some period of time. So to counteract that, the developed world should be moving faster. It's a notion in the UN negotiations known as common but differentiated responsibility, right? Climate change is a global challenge. We all have a common responsibility to tackle it, but that responsibility is differentiated by the means and the situation that different countries find themselves in, as well as their historic responsibility to cumulative emissions, of which the United States is the largest contributor to cumulative greenhouse gas emissions. We use these numbers like 1.5 degrees or 2 degrees, which are obviously nice whole numbers, but they're arbitrary values in a lot of ways, right? They're backed by some science, but they're not hard thresholds in the geophysical system that we sort of tip over and then things get out of control, right? So this is a graphic from the same IPCC report that shows the gradient of impact, just sort of as a visual depiction of the rough kind of transition zones that we're likely to encounter across a whole number of different important Earth systems that we care about. And the reality is that we have some confidence, these are the confidence levels, very high, medium, low, and where that threshold lies. So some systems we know very clearly when we start to drive fundamental changes. Others we're sort of uncertain about what the range looks like. But in reality, there's no sort of single cutoff. Every 1/10 of a degree matters. And the warmer it gets on average, the more damage occurs to various ecosystems, to important human factors like crop yields or heat-related deaths from heat exposure. Productivity loss and outdoor economic activities like construction and agriculture is an important one. So there's a whole number of these impacts, and really the challenge is to get to zero emissions as rapidly as possible. Right? And so if we hit 2 degrees, that's better than that's better than 2.1. If we hit 2.5, that's better than 2.6. Better than 3. So I just want to leave that context. There's been a lot of discussion in some of the public media about we have 10 years to confront climate change or all hope is lost. In some ways, it's true. If we don't do anything over the next decade, then it's going to be extremely unlikely that we'll hit any kind of stabilization target. But that doesn't mean we need to get emissions to zero in the next 10 years. What it really means is that if you look at the IPCC report, is that we have 10 years to get our act together and to start driving emissions downward to be on the trajectories we need to stabilize emissions at anywhere between 1.5 and 2. Any questions about that challenge? Okay. So where does electricity fit into all this? Well, this graphic shows the US picture and the global picture for total greenhouse gas emissions, not just carbon dioxide, but others as well from different sectors. So you can see that in both the US and globally, electricity production is about 1/4 of the overall emissions pie. So if we want to get to zero, we have to eliminate all of these, but the electricity sector is in many cases, the biggest one in the United States, thanks to improvements in electricity sector emissions and lagging improvements in the transportation sector. Just recently, as of about 2017, the transportation sector edged ahead of electricity. It used to be the biggest, and now it's the second largest. But if you look globally, it's still the largest source of emissions from any individual sector. Right? So big part of the solution. But even that doesn't quite tell the story, because electrifying and powering economic activities with clean electricity is an important part of solving the other 3/4 of the pie. Not all of it, but a big chunk of the other 3/4. So I'll show you what that looks like. So this graphic shows a couple things. The first is our current electricity supply here. This is our supply from natural gas and coal, which represent together about 60% of US electricity generation as of now. And then we get about 20% from nuclear and another 20% from all of the renewable sources. The blue is hydropower and the green is the remaining renewable sources. So just this last year, total wind power production exceeded hydropower for the first time. So they both provide about 9% of our electricity. And if you add solar, geothermal, biomass, it's another couple percent. So in total, it's about 20% from renewables, 20% from nuclear. So 40% of our electricity from carbon-free sources today, and 60% from fossil sources. Right? Then if we go through time, the bars show how we need to change the existing installed capacity by retiring fossil generation to be on track to get to net zero emissions of greenhouse gases in the US by 2050. This is from modeling done for preliminary results from a study ongoing here at Princeton called the Net Zero America Plan, which is a strategy to look at several different pathways to decarbonize the overall US economy that we're currently conducting. And so you can see that the first thing that happens is this black chunk from coal goes away over the next decade. So the fastest, cheapest thing we can do to reduce emissions is to get rid of all the coal generation. We can do that at basically zero cost in terms of direct impact on electricity rates and an enormous net benefit in terms of public health. Because coal is both particularly carbon intensive and a major source of public health impacting pollutants like particulate matter and NOx and SOx emissions. So sulfur dioxide, which causes acid rain. So we can knock this out and replace it with a mix of gas and renewables for basically net cost, zero cost at this point, and a positive impact on societal benefits. So that's the first order of operations, and that gets us, a good chunk of emission reductions over the next decade. Over time later, we then have to phase out all of our existing natural gas plants or convert them to run on carbon-free sources of gas, whether that's from biogenic sources or from hydrogen produced from renewable fuels or nuclear power. So then the bars, the lines up top is the other half of the challenge, right? So this is the bars down below show us what it takes to eliminate that quarter of our emissions from electricity generation. But the blue lines show what it takes to electrify all the other activities we need to help decarbonize the overall economy. So that's the increase in total electricity demand, or that is the total electricity demand in blue, and then the increase in percent terms on the edge by 2050 as we expand the role of electricity in powering our economic activities. So we would need to electrify a large share of our automotive fleet, even heavy-duty vehicles or medium-duty vehicles like trucks for shipment. We have to shift from natural gas consumption and oil consumption for heat in buildings to electric heat pumps or ground source heat pumps. And we need to electrify a number of industrial activities that can use electricity as an input instead of combusting fossil fuels. That doesn't eliminate all of the problem. It solves, about 50 to 70% of the emissions challenge, depending on the scenario. But what it does do is it leads to over doubling of total US electricity consumption between now and 2050 on that pathway. So electricity is going to play an increasingly central role in our overall economy if we were going to decarbonize the economy. And that's because we have a number of cost-effective substitutes for electricity generation from carbon-free sources: wind, solar, biomass, nuclear power, carbon capture and sequestration on fossil fuel power plants. And we lack many of those substitutes in other sectors, right? There's not a lot of easy ways to make large amounts of carbon-free liquid fuels to power transportation, to make gaseous fuels to stick in pipelines for pipeline gas needs like heating and heating industrial processes. So the challenge is to eliminate as much of that as possible, those liquid and gaseous fuels, by swapping in clean electricity, and then that gets the total remaining amount of carbon-free gaseous and liquid fuels down to a manageable level that we can supply with carbon-free substitutes like biogas, so methane from biological sources, or production of synthetic liquid fuels from hydrogen and carbon dioxide from either direct air capture or from biomass sources. Yeah, so we ran four scenarios. I'm only showing three on this chart for this case. So the unconstrained just sort of lets the model pick what it wants to do. We all then have another scenario where we delay the electrification uptake. So it's very aggressive rates of electrification. We would need to be at like 100% of light duty vehicles sold are electric by like 2032 or something like that to be on that track, and huge heat pump uptake in buildings. So instead, we also ran a delayed electrification scenario, which is the one that kind of curves up more slowly in blue. And then we added a scenario where these scenarios rely heavily on renewables build out. I'll show more of this later in the semester, but so the pace of renewables build in the models is way faster than we've ever seen historically. It doesn't mean we can't do it, but we're talking about like rates in the US that are equivalent to the fastest single global total deployment of wind and solar that we've seen sort of worldwide. So we ran a case where we constrained the build rate for renewables as well to the fastest single year in the US that we've seen for wind and solar. And then that relies more heavily on natural gas and with carbon capture and nuclear in that scenario. And that just slightly adjusts the electrification rate that makes economic sense. Yeah, so it's not in here because we don't have any current CCS at like 2 plants. But it is part of the solution. So the gap then between the bars and the line is the amount of new clean generation that we need to add. And I'll show you what that looks like in a second. And that's where carbon capture and sequestration can help, where renewables plays a central role, and where the growth of nuclear can help as well. So I just wanted to first point out that in our delayed electrification case, right, we said we're not going to electrify as much of the end use activities because people, consumers are going to be slow to buy electric vehicles. People don't want to switch to heat pumps in their homes because they're unfamiliar. And if you miss the sort of stock turnover, the fact that when you go to buy a new car, that's your car for the next 5 to 15 years, right? And so if you miss the turnover rate, if you build a new boiler in your house, an HVAC system, that might last for 15 years. So if you kind of miss the timing of the stock turnover for people, they're probably locked into whatever purchase that was until the next time they need to upgrade something. And so the delayed electrification case substantially reduces the amount of end-use activities that are powered by electricity. But the interesting thing is, you can already see this on this chart, is that that's the darker blue and the lighter blue towards the top, is that the only substitute for electrifying end uses that the model chooses is just more electricity. So counterintuitively, if we don't electrify end uses, which is what we see here, this is the final energy demands that are powered directly by electricity. And then this is the light electrification case where it's reduced by, say, 20%. We end up actually having to make more liquid and gaseous fuels, right? So we need more motor fuel, we need more jet fuel, we need more natural gas substitute for pipeline gas. And the only way to really do that is to rely more on electricity, to both produce hydrogen from renewable sources, powering electrolysis, and to pull a little bit to pull CO2 out of the air with direct air capture technologies that run on electricity as well. And then we take the CO2 from the air and we take the hydrogen from renewables and we combine them, which takes more electricity, to make hydrocarbons, to make gas and liquid fuel substitutes that we can drop in and power the remaining portion of our end use activities that aren't electrified. You can rely on biomass to do the same thing, but all these scenarios basically tap out all the available biomass before you get to this level. And so then on the margin, the only thing you can do if you fall short on electrifying end uses is to supply liquid fuels and gaseous fuels using intermediate electricity demand. And so what you can see is that leads to very little difference in the total amount of electricity consumption. So there's really no way around the twin challenges of building a huge amount of new carbon-free electricity to decarbonize what we have, and then basically doubling our overall electricity supply to power more activities in a carbon-free world. So electricity is the linchpin in our efforts to decarbonize and confront climate change. This is the total build out of new clean generation, assuming that we keep all of our existing renewables and half of the existing nuclear fleet through to 2050. So this is the gap between those blue demand lines and the bars over time in the previous graphic. And it's the total amount of new clean electricity we need to be building in the United States to be on track to net zero emissions by 2050. And so I overlay that with a couple lines. The first is all current generation from carbon-free sources. This is all nuclear, wind, solar, biomass, geothermal, and hydro. Again, that's about 40% of our electricity. So between now and sometime between sort of 2027 and 2028, we would need to double all of our current electricity supply from carbon-free sources to be on track. Then the red line is total US electricity generations. This is the entirety of all generation sources in the grid today. It took us 150 years to build that system. And we would have to build that entire system again from clean sources sometime between now and 2037 or 2041, depending on the electrification track that we're on. So over the next 2 to 3 decades, we're talking about rebuilding the entire US electricity grid. And then, depending on the pace of electrification growth, because demand is doubling, we have to do that nearly, that entire thing again, basically, and build the entirety of the grid once more over the next 2 decades, 1 to 2 decades. So this is an enormous challenge. I'm not going to say this is trivial. I'm not going to say we can do this. We probably could, but we're not on business as usual track to do this at all. The bars down here. So I've converted this growth rate to the amount of average generating capacity you would have to bring online. I say average because certain power plants produce at different amounts of utilization throughout the year. So a wind farm, because of the variability of the wind, might only produce at 30 to 40, 45% of its capacity on average throughout the year. Sometimes it's at 100%, sometimes it's at 0, and on average it's about 35 or 45%. So we call it the capacity factor or utilization factor for a technology. Conventional power plants could run all the time, but because of economics, they tend to not. So the higher the fuel cost the technology has, the less often it's worth running it. So a coal plant runs more often than, or a nuclear plant runs more often than a coal plant, which runs more often than a gas plant traditionally. So this is the average gigawatt. So if you sort of take that capacity, the maximum it can produce, and multiply it by its utilization rate, this gives us sort of a unifying metric to compare across technology. And what we need to do is bring online an average. There's some change across time given these aren't directly linear, but an average of 28 to 35 gigawatts, average gigawatts of new generating capacity. How big is a gigawatt? A gigawatt is enough to supply about 1 million US households with their annual electricity consumption for the year. It's a lot of energy. It's about the output of a large single nuclear power reactor, most of which are around 1,000 to 1,400 megawatts. So they're in that gigawatt scale. Gigawatt is 1,000 megawatts. So, it's talking about basically bringing on enough clean electricity to power 28 to 35 million households, or 28 to 35 new nuclear power plants worth of production every year. How have we done historically? Well, those are the bars down below there. So the first green bar is the average build rate for new renewable energy sources over the last decade, 2010 to 2018, which is the last year I have annual data for. Where we brought online the average of 3.4 average gigawatts of production. So 3.5 roughly nuclear power plants worth of wind and solar production. The single fastest year of combined non-hydro, this is not including hydropower because we're not expanding that. The single fastest year of combined non-hydro renewables, so wind, solar, biomass, et cetera, was 5.3 average gigawatts. So we need to be going sort of 6 to 7 times faster than the fastest year that we have on record in the US to be on track for this. And if we look beyond renewables to the build out of nuclear power in the 1980s, the fastest sustained average decade that we brought online nuclear, if you adjust for the larger population in the US today, which you could adjust for population or GDP, thinking that we have a lot more resources available to us today than we did in the 1980s, then that was the equivalent on population weighted terms of 7.4 average gigawatts. That was sort of the fastest decade-long sustained rate that we've ever brought online new carbon-free sources of electricity. Okay. So we're not on track to do this yet. This is going to require a shift, a fundamental shift in policy, fundamental shift in regulation, an enormous shift in what gets built in this country. We're moving that direction. I think roughly half or 60% of all new capacity built in the last few years has been wind and solar. But the remainder is still new natural gas-fired power plants, which are not part of this solution. Okay. So this is a huge undertaking. It's going to fundamentally transform the way we make and use electricity if we're up to the task of tackling decarbonization. To give some other global contexts or other non-renewables related contexts, these are the 3 different rates in red from our range of scenarios, 20 to 35 average gigawatts. And then if we look across other examples, Germany is one of the world leaders in bringing online renewable energy. And if we adjust each of these per capita to make a kind of equivalent metric across time and countries, Germany's fastest peak year was about 12 gigawatts, so about double our fastest year. And its average was about 6 gigawatts. So Germany's going about twice as fast as we are in the United States on the population weighted term. But even that's still, a third of the pace that we would need to do here. And then the fastest build out of any technology in the United States is actually natural gas fired power generators in the 2000s. That was right when we restructured our electricity markets to be competitive and allow new entrants. We'll talk about that in the second half of the class, the second half of the semester. And that's when we built a huge amount of natural gas fired generators, combustion turbines, combined cycle power plants. And on average terms, that was about 23 average gigawatts. So we're starting to get in the ballpark of what we need to do. The peak single year, I think, was something like 54 total gigawatts, not average, but huge amount. It's a lot. We have about 1,000 gigawatts of total generating capacity in the US. So 50 gigawatts a year is a lot. And then if we look at the fastest clean energy additions or carbon-free energy additions globally, those are Sweden and France bringing online nuclear in the 1980s, where they brought on between 26 and 29 or 30 average gigawatts a year, but only for a decade. We have to do this for the next 3 decades. So at least there's some hope that, if you get your country organized or you get your markets organized and flood it with private investment, as in the case of the natural gas boom, that we can see deployment on this scale. It's not something we've seen sustained for 3 decades, but we can at least see average decade-long expansions of clean energy or natural gas that look something like what we're talking about. So it's not physically impossible. We have enough resources. We have enough investment potential to do it, but it's only going to happen in the case of a particular alignment of either market and policy conditions, as in the case of the US natural gas boom, or a state-led effort to build out these things, as in the case of Sweden and France in the 80s, where these were national utilities owned by the government, picking a single nuclear design and building a bunch of them over and over and over again for a decade. Yeah, so it's their average average capacity, which if you multiply by the number of hours in the year gives you the generation. So they're equivalent. If you're talking about the actual capacity of the resource, you then need to multiply or divide that by their capacity factor to get the total amount. So if you wanted to do this with wind, at say a 35% capacity factor, you need to multiply the deployment rate by 3 to get the total amount of capacity. Yeah, for wind or solar. So I try to use average gigawatts so that we kind of can compare across technologies. Is there another question over here? I saw here. Okay. Yeah. Yeah, so China, if you do in per capita terms, doesn't really rate on here because of the large population. But if you do it in per GDP terms, which is another normalization metric, the coal boom in China is easier. So it's similar in per capita terms of what we need. So China has built an enormous amount of coal-fired capacity between 2005 and 2018. And that pace of build out is comparable in GDP terms to the scale that we're talking about, but of course it's coal and not clean energy. Wind and solar also, if you take the in per capita terms, their build rates for wind and solar are the fastest in absolute terms. And then if you scale for GDP, they're also quite large. So that I could add those on here in the future. But these are population weighted, and so when I did the China math, they were small because the Chinese population is so large. All right, so that's kind of daunting. Well, let's talk about some good news at least. This is the average cost of generating electricity from wind and solar in the red and blue. And on the other axis, the cost per capacity for lithium-ion battery packs per kilowatt hour storage capacity in orange. All of which have dramatically declined over the last decade. Right? So wind has fallen by about 70%, and lithium-ion battery packs and solar by basically 90%. They cost 1/10 of what they did just a decade ago, which is just remarkable. And what gives us the political space, I think, to even talk about net zero goals. Right? All the Democratic primary candidates have embraced net zero emissions in the US by some date, 2040 to 2050. The state of New York was the first I should say Hawaii. I always forget Hawaii because it's off there doing its own thing. Hawaii in 2018 and New York last year passed legislation committing their states to get to net zero emissions of greenhouse gases across the whole state. So the first legislative requirements for that in the United States. A number of other jurisdictions have enacted executive orders to do so, including California and Massachusetts. Here in New Jersey, they've committed to 100% carbon-free electricity through an executive order, not yet economy-wide. The goal is still 80% reduction economy-wide, but moving in that direction as well. And about 15 other countries, including the UK and France, have also committed to net zero goals. So starting to commit to these dramatic transformations, even though they require the kind of pace of change that I talked about before. And the reason that we're even in a space where we can have that conversation, I think, and talk about these bold goals and not be laughed immediately out of the room is because of this decline in the cost of wind, solar, and batteries. I used to work as a renewable energy advocate, a policy advocate, before I went into academia. From 2006 to 2008, I worked in Oregon, where I helped pass the Oregon Renewable Energy Act, which was a law that required the utilities there to get a quarter of their electricity from clean sources by 2025. That was seen as a huge, bold goal in 2007. And that's because back then, the cost of electricity from a wind farm was over $100 a megawatt hour. And from a natural gas plant was something like 40. So we're talking about a huge premium to try to use these alternative energy technologies that they were considered at the time. These are these funny little alternative things that we just built a few of. And solar, forget about it. It was off the charts. We didn't even, provide any policy support for solar. We said, well, you guys can just duke it out, and if solar gets cheaper than wind, fine. But the goal is just renewable energy. Find the cheapest way to build it. And we assumed at the time that would all be wind. Then something dramatic happened, right? Policy support like that policy and numerous others throughout the world drove the dramatic increase in the deployment of these technologies, which drove a huge investment in their manufacturing capability, particularly in China, progressive improvements in process innovation and incremental improvements in the efficiency of these cells, and larger scale turbines that could produce more power for lower cost. And that drove this huge decline in the cost of the technologies over time. So that now, across much of the country, wind and solar are the cheapest way to generate electricity of any new source that we could build. They're actually cheaper than a new natural gas-fired power plant, which was just like if you told me that in 2007, that within a decade we would be talking about that, I wouldn't have believed it. Right? These are faster than even experts and advocates like myself expected.
Does levelized cost of electricity, does that account for subsidies?
No, this is the unsubsidized levelized cost. Yeah, this is without subsidies. So subsidies make it actually cheaper than this in the U.S. for private companies.
Yeah, but natural gas is also, or fossil fuels are also subsidized.
They are, but the impact. So the total volume of subsidies for fossil fuels is actually starting to get close to the renewables volume is going up, so they're about equivalent now. But the impact per unit of energy delivered is quite small because we produce so much natural gas. So if you took the subsidy away, the impact on the price of gas would be actually pretty small. Whereas if you took the production tax credit away from wind, it's $21 a megawatt hour. So it's about half the levelized cost. Much bigger deal. But yeah, it's true that everything's subsidized to some degree, which shifts the playing field, but this is a unsubsidized cost. And this is for a single location. Obviously, the average cost of electricity you produce from a wind farm depends on how much electricity you produce, because all of the costs are upfront and fixed in the form of capital. So a more productive wind site will have a cheaper cost, and a less productive will have higher. So there's actually a big range across the country for both solar and wind, but this is an average figure for a good commercial site.
Levelized cost. And the second question is, what accounts for this very sharp drop that you see from 2009 to 2011 in solar? Is that one or two things? Or
Yeah, good question.
multiple different developments?
Yeah. So levelized cost of electricity is just the average revenue you have to earn for every megawatt hour you sell to pay off all your costs, both your fixed costs and any variable costs, and in the case of natural gas or coal, fuel costs. So it's just a measure, general measure of how much revenue you need to earn per kilowatt hour that you sell. Now that's important to note that this is only the cost side of the equation, right? Cost has to be less than the value you deliver. And each of these technologies delivers different value. Okay, I have a stump speech on this that you might have heard if you've come to some of my lectures, or public lectures. I'm giving one next week at the Bradford seminar at the Wilson School, where I'll go into this cost versus value thing. But cost is not value, right? So a wind farm might deliver more value than a solar farm, but less than a nuclear farm. So you can't just compare them directly like this. So it's better to just use it to compare it for an individual technology, both the trend over time and its cost. And this gives you basically the benchmark you need to clear for how much revenue you need to earn, either from subsidies or from selling electricity to cover the cost of the profitable. Now, why did this get so much cheaper? These years is basically the China story. So continues before this, actually, if you go back a few more years. Germany, the United States, Italy, Spain, a bunch of countries had pretty aggressive policies to support solar that ramped up in the late 2000s. Many of those were motivated by the idea that those countries would build their own domestic manufacturing base to build solar, particularly in Germany, where they have an advanced manufacturing sector. But China during this time period, which was the recession, remember the global recession, made a huge amount of capital available for basically free for provincial governors to loan out to state-owned and not in private companies to build huge solar manufacturing facilities. Gigafactory, you probably heard of the Tesla Gigafactory that's putting together batteries at a gigawatt scale in Reno, Nevada. Well, they built dozens of gigafactories worth of solar production capability in that time period. And so that did a couple of things. One, it captured big economies of scale from going from, say, making 100 megawatts a year on an assembly line to making 1,000 megawatts a year or more. They also, because it was an extremely competitive environment, the price was falling rapidly. It drove a lot of incremental process improvement in automation and manufacturing, and a little bit of improvement in cell efficiency and module efficiency. So this is mostly a manufacturing story and less a R&D story, although there's a little bit of that going on. If you go back further in time, there was a bigger role for R&D. And if you're really interested in diving into the whole history of this, I can recommend a great book by Greg Nemeth from the University of Wisconsin. He was here as a speaker at the Andlinger annual meeting, if any of you came, that he just put out on how solar got cheap. So it tells the 3-decade story of how we got from, stuff that you could only NASA could afford to put up on satellites because it was literally the only way to get electricity in space, to something that that we are generating large amounts of electricity from in a competitive market today. It's a great book. It goes through all the different needs and stuff. So I'll leave it at that for now if you want to dive in. Grab Greg Nemeth's book, or he has a couple public lectures online too.
The levelized cost depends on the lifespan of the plant, right? Since wind and solar are relatively new technologies, do we have good data on how certain are we that we know what the lifespan of this plant is?
Yes, it's a great question. It depends on the financial lifespan. So think about a mortgage for your house. Probably most of you don't own homes, but your parents probably did. The house might last forever, right? I mean, it would be 100 years, 200 years old house. But when you buy it, you take out a mortgage for some period of time, usually a 30-year standard mortgage, maybe less, maybe more. And so what drives the levelized cost is the fact that you have to collect that mortgage payment for the wind farm or the solar farm, same idea. It's an annuity of your fixed cost over the financial life of the product or the asset. Most wind and solar farms are financed over a 20-year period generally, sometimes 25, sometimes 15, but it's that financial life that determines how much of the fixed cost goes into every year that you have to recover. The wind farm might actually last for much longer than that, but it doesn't affect the levelized cost unless you include some sort of scrap value at the end, or residual value after the asset is paid off.
But if you knew the wind farm was going to last 40 years, then that would effectively, if you took your mortgage out for that long,
if you could get a loan, right? I mean, a house lasts for 100 years, but you can't get a 100-year mortgage because the banks don't want to give you one. So it depends on what access to capital you have. So generally, for independent power producers and others, those are amortized over shorter time periods. The same for nuclear. Nuclear plants could last for 60, 80 years, but generally they're amortized over 40. And that's only when they're regulated. If they're a private one, they're amortized over 30. So there's a difference between the financial life and the asset life. The other thing is that when you're talking about beyond 30 years, you're discounting the future value. And so going from 30 to 40 years actually has a smaller impact than you might think, because those future cash flows are discounted dramatically. So yeah, but yeah, it does matter in the lifespan. In practice, we've seen the solar last a long time, right? Solar farms, they degrade slightly due to photoelectric effects, but they last for decades. Wind farms have a lot more wear and tear. The early ones broke fast, but the commercial ones that we're building now are warranted for at least 20 years, and they'll probably last longer than that. So this is good news. We have cheap wind, solar, and batteries. And I say that's good because I think, if we look at our modeling results from the net zero study and others, these are going to be the star players in our decarbonization, right? Star point guard, women's teams. But unfortunately, they're not going to fill out the whole team, right? So you can do really well if you have one really good star player, but championship teams have 5-star players on every right position on the court. So wind and solar and batteries might be 2 or 3 of our stars. We got to fill out the rest of the team. This is what the whole team looks like based on my research. Colleagues at MIT and I put together this sort of taxonomy of different low carbon technologies that you need to fill out the overall portfolio. And they include the renewables up here, which we call fuel saving technologies. Fuel saving because they deliver most of their value because they have all capital costs and free energy. Right? So when the wind is blowing, the water is flowing, the sun is shining, you get free electricity. And that means that when we use wind and solar, we displace something else that has a higher fuel cost, like a coal plant or a natural gas plant. And so the value that that delivers is primarily in saving that fuel, the value of that fuel or the cost of that fuel, including the criteria pollutants and emissions and everything that goes along with that from a societal perspective. However, because they're variable and intermittent depending on the weather, we can't really rely on them much for what's called firm capacity. So it means that you can't really shut down the reliable power plant that you can turn on and off whenever you need it, just because you have an equivalent amount of wind or solar. At initial penetration levels, they have a reasonably high capacity value, substitution value. But at high penetration levels, the times we need the most firm or reliable capacity is exactly when the wind isn't blowing and the sun isn't shining. Right? So the periods when we have very low output from these facilities. And that means that even if we added a huge amount of capacity, during the hours when we need firm generation, they'd be producing very little because they're, it's very weak and it's nighttime. And so at the limit anyway, at higher penetration levels where these are dominant sources of energy, their capacity value falls pretty close to zero. And that means that we need other technologies from the other two wedges to replace our natural gas and coal capacity, even if we can displace a lot of the energy they produce with energy from wind and solar throughout the year. Okay. Then the blue wedge includes what we call fast burst or balancing resources. These are technologies like batteries, lithium-ion batteries in particular, which we're deploying a lot of now to the grid. Also rescheduling flexible demand. So, things like when do you charge your electric vehicle or run your irrigation pump or run heat, certain industrial boilers or things like that. And then demand response or price responsive demand curtailments. This is sort of price elastic demand, economic framework where you might be willing to pay a certain amount to consume electricity, but once it goes above a certain level, you might be willing to turn off one of your air conditioners or turn it down a couple degrees or stop an industrial process because you're getting paid enough to stop doing it. It's worth it to stop using the electricity input, like for an aluminum smelter. So that's called demand response. And so all three of those things are really effective at providing short-term bursts of power. So they have a lot of capacity value and they have a lot of flexibility, but you don't want to sustain them over a long period of time, right? Your battery eventually runs out of juice. You don't want to stop consuming electricity for weeks at a time, even if you're willing to turn off your air conditioner for a couple hours. And you can reschedule when you charge your electric vehicle, for example, within the nighttime, but you're going to need it charged to go to work the next morning. And you're not going to be willing to defer that for several days. So these are things that are primarily good at balancing within a diurnal schedule in the daytime. But that's great for, say, moving the solar peak production with storage from 12 to 5 p.m. or shifting when we consume electricity by charging our EVs when it's very windy or very sunny during the day. What that leaves then between the two of those is a critical gap for a technology that's always available any time of the year for as long as we need it, irregardless of the weather. That's what we define as a firm technology. It's firm if it's not weather dependent, it's not energy constrained, and it can produce energy any season for as long as you need it. That's what we rely on natural gas and coal-fired power plants. And remember the few slides back, we need to get rid of all those coal plants within the next decade and all the natural gas by 2050. So we need something that can replace it. And the candidate list of technologies are geothermal, renewable sources like geothermal and biomass, and non-renewable sources like nuclear or coal or gas with carbon capture and sequestration. We take the CO2 emissions and instead of venting it into the atmosphere, we sequester it deep underground where it's permanently stored. Right. The other option is to produce zero carbon fuels from one of these other sources. So from renewables, producing hydrogen from electrolysis, nuclear doing high temperature electrolysis, or taking biomass and gasifying it and turning it into other fuels. And those we could run in our existing gas plants or in new gas turbines. There's a couple technologies on the borderline that, depending on their characteristics, can play this role if they can produce energy over long enough periods of time. That includes large reservoir hydro facilities, so big dams with huge lakes that can store months worth of energy, and potentially very, very low cost, long duration storage technologies. It's an area that I'm actively researching now. And I'll just say that it requires costs that are roughly 2 orders of magnitude cheaper per kilowatt hour of storage capacity than typical batteries that play the fast burst role. So you want to use a battery every day, you cycle it 300 times a year. That means that every time you run it, you get a little bit of money and you can pay off a much higher cost. Long duration storage might only cycle the extra, last unit of capacity you build once or twice a year. And that means it has to be extremely cheap to make enough money in those, few times you run it to pay off the capital cost. And so from an economic perspective, long duration storage that provides several days or weeks or even months worth of energy storage to replace the firm generation can only function economically if it has costs on the order of $1 to $10 a kilowatt hour, whereas batteries today cost $200 to $300 a kilowatt hour. So we're talking about very different technology. This could be producing hydrogen and storing it in very large underground storage patterns like we do for natural gas and seasonal storage. A few small short list of other technologies that might fill the bill there, but it's a challenging one. Yeah. No, pumped hydro generally is several $100s a kilowatt hour. The lowest is maybe 50. You already have a lower reservoir that's natural, and you just need to build the upper one. And it's generally they're sized to be, generally daily cycles. They're built to do 8 to 12 hours of duration. Some of the biggest ones are like 2 days worth, but they're not really the seasonal. Yeah. No. That's a great question. I should always say that. I forget usually. These are indicative. So when you run the model, the optimization model, the sizes of the wedge from both an energy and a power capacity, which are different, shift around. If you look at the paper this came from, which I can is on the resources at the end of the slide deck, which I'll post online, we run a ton of different cases, and there's different shares of each of them. The power capacity needed from these sources is fairly constant across cases. The energy capacity changes a lot depending on their relative costs, the energy generation share. Okay, I'm going to press ahead through a couple other things because we're getting close to time. All right, so that's the climate challenge, big enough. I mean, that alone, I think, is reason enough to take this class and focus on the role of electricity, but that's not it. There's also the role of distributed generation, which is having an enormous impact across many different markets. This is a neighborhood in Germany where you see solar on every rooftop, but it could as well be New Jersey, where we have a huge amount of distributed generation from solar as well. This graphic shows the rapid growth in distributed energy resources just over the last few years. So this is total installation of solar PV in the US. And you can just see the sort of rapid cumulative, this is the cumulative, this is the annual, this big surge just in the last 5 years of solar deployment in the US. We're now at over 2 million households or businesses with rooftop solar systems in the US. We hit the 1 million point just a couple years back. This is moving very quickly. If we think about the total energy generation from distributed solar, so this tries to separate out big 100 megawatt or larger utility scale solar farms, much of which we're building in the West. And you look at just the distributed stuff, so the things that are on buildings and ground mounted, small systems you might see at the corporate parks along Route 1 around here. And we look at the share of overall generation. Nationally, it's only about 1%. But there's a great William Gibson quote, is one of my favorite sci-fi authors that is often repeated, that the future is already here, it's just not evenly distributed. So the same is true for solar, right? So the distributed energy future is here, it's just not evenly distributed. So it's concentrated, even though it's only 1% nationally, it's almost 10% of electricity from distributed solar in Hawaii now. 6.5% in California. When I just updated this slide, when I presented this about a year and a half ago, Massachusetts is only 4%. Now it's up to 3.5%. Now it's 7.5% just a year and a half later. So this is moving really fast. And New Jersey is about 5% of our electricity from distributed solar. So these are starting to become material, shares of our total generation. Remember that nationally, hydropower is only, and wind are only about 9% of our generation, nationwide. So, in certain regions, we're talking about similar scale of importance. And this is just something fundamentally new. Previously, we've had a few thousand generating units in the country. Now we're talking about millions that are each controlled by individuals like you or me or businesses and are responding to totally different incentives than the typical incentives that a commercial power plant or a regulated utility would respond to. Plus, they're generating electricity on our distribution networks, which are never really designed for supply of electricity two directions, right? They were designed for one-directional flows from big bulk generators in transmission down to distribution, down to households at low voltage. Well, now that household isn't just a consumer, it's also a small power plant. How do we manage all that from a technical perspective? How do we design incentives so that when you decide to, when somebody knocks on your door from Momentum Solar and says, hey, I've got a deal for you, let's put solar on your roof, the decision that you make that's in your financial interest is also in society's interest. It's also in the grid's interest, which is not the case today, as we'll learn later in the course. No, it's a total. Well, that's actually a good question. This is prior to Pilgrim closure, so this is 20. That's a good question, actually. It might be because Pilgrim closed. That's a good point. Yeah, so Massachusetts retired one of its large nuclear reactor last year, which might be moving the denominator down. It's also growing rapidly because we have a very aggressive subsidy environment. So the reason these are different is largely because the subsidy regime in each state is different. And certain states have set very aggressive subsidy regimes. Hawaii is somewhat of an exception. It's because their cost of electricity is so high because they burn imported diesel for much of their electricity. So the rates in Hawaii are several times higher than much of the country. But these states are sort of a combination of high retail rates for electricity, a policy known as net metering, where we pay people for generation exactly what they would pay for consumption, which is not, as we'll learn later, is not reflective of the actual cost of electricity, and subsidies. So we pay in Massachusetts and New Jersey something on the order of $200 per megawatt hour, $150 per megawatt hour for electricity produced by solar, whereas the average wholesale rate for electricity is on the order of $30 or $40. They're paying an order of magnitude more for stuff, so people build it. It's a good deal. And the total cost of these policies is no longer trivial. When solar was 1%, it wasn't a big deal how much we were paying. But when solar gets to be 10% of your electricity, it matters a lot how much you pay per kilowatt hour or megawatt hour. So these are the total costs as of several years ago in many cases of the solar rooftop, the Million Solar Roofs program was the informal name, or the Go Solar California program, which spent several $100 million over that time period, about a decade, to get solar up to a few, 4 or 5% of California's electricity, and it's grown from there. Now, because all that rooftop solar is generating a lot of electricity that's flowing backwards onto power lines that weren't really built for it, we're also have a new program that encourages behind-the-meter storage, so people to install storage systems in their homes to soak up that energy and not export it onto the grid. So to sort of fix the problem that the other subsidy created, and that's costing already $166 million a year for those storage systems. Yeah, it's a blend of individual households and the commercial and industrial market, and each state has a different ratio of that depending on the subsidy regime. The total number of systems at the residential level is many times larger because they're small. There's a lot of them, but the total generation share, I think, is about 60-40 residential, and then commercial and industrial is about 40%. But that varies by state. Well, so unless you want to disconnect your whole home from the grid and try to supply all your electricity from solar and batteries, which is extremely expensive, everybody is connected to the grid. So with the exception of sort of out in the backwoods somewhere, off-grid systems, these are all grid-connected programs. So when they're generating more electricity than they consume, they're exporting it into the grid. And when they're consuming more than they're producing, they're importing power from the grid. So we have to have a regime in place to manage all that. Both physical interconnection rules, you can't just go and plug it into the grid because it causes challenges. So there's interconnection standards you have to meet in every region, and those differ. And then there's some kind of payment regime established for how that gets compensated. And that's where the regulation comes in. So this is a great example of intersection of engineering, economics, and regulation all driving how these decisions work. Yeah, it depends. Yeah. Yeah, we'll come back to that later. That's a great, and each state is a little bit different, but largely, yeah, you're getting at it, which is it's a difference in politics, right? Yeah, usually there's some cap, but that cap keeps getting raised in multiple places. So yeah, often it was like we're only going to do so much, and then we get that limit, and then they raise it, and then they raise it again, and they raise it again because it's popular to support. Yeah. In New Jersey and Massachusetts, we're spending several $100 million a year alone, and these are much smaller states than California. So these are pretty big sums. In fact, in New Jersey, they've realized, in both states, they realized they had to fundamentally reform these policies because they were financially unsustainable. So now in Massachusetts, they just launched a new program that they call SMART, that I don't consider that smart, that replaced the old ones. It is better than the old ones, it's not quite great. And it's trying to keep this cost down to a more manageable level. And same with New Jersey, they're phasing out the current subsidy program and replacing it next year with a new one. So those are the cost side of things, and I don't want to just hammer on the costs, but it's important to recognize there's also additional value that these technologies deliver. So generating energy closer to where we consume it is generally a good thing. It means we can avoid a lot of costs related to the electricity distribution and transmission networks, and we can spare land, right? So building a solar system on a rooftop is a lot better, the rooftop's just sitting there not being used, than building in the middle of the desert or even on prime agricultural land where we're using farmland to install these large, solar farms. So the benefits to distributed generation all come from their what I call locational value. The fact that certain attributes of energy systems value are dependent on where you are in the system. Other things are not. They're fungible. It doesn't really matter where you produce them. But these all arise from the network effect. So avoiding transmission and distribution losses when we deliver energy from generating sources to consumers. The closer you generate to demand, the lower the losses are. You can avoid those losses. That means that a megawatt hour produced at your household is worth more than a megawatt hour produced far away. Also, you can potentially avoid network congestion or constraints in the distribution lines and transmission lines, or upgrades that would otherwise have to happen to accommodate, say, the import of energy from a wind farm or a solar farm very far away. Now, you have to be generating power in the right location at the right time when that constraint is active. But if that's true, you can avoid those upgrades, and those can be very costly. So that's a big potential source of value. In some cases, you can improve local reliability. So microgrids that are able to island and continue to supply power locally when the grid is disrupted, or household systems that you can shut down your grid connection and power your own house, deliver improved reliability. And you can't do that with a wind farm or solar farm that's very far away because the network between you can go down. However, most systems don't do this. Most grid-connected solar systems are designed to automatically shut off as soon as they lose grid tie, because you don't want a line worker going down the line trying to figure out where the outage is, getting electrocuted because the household is feeding power back into the grid, and they thought that it was de-energized because there was some break upstream. So there's a safety rule. So unless your solar system is designed for self-islanding and has a battery that you can run it off of, most solar systems don't actually provide any local reliability benefit. They could, but they're not designed to do that. I'll point out also that some of these technologies are inherently distributed. So I consider flexible demand to be the most valuable distributed energy resource because it's relatively low cost. It's already there, right? We're already consuming electricity at the point of consumption. That's by definition. So when we choose to charge our electric vehicles, or how we operate smart thermostats, or how we change industrial processes that have thermal mass that we can move around in time, is a very important potential value source of locational value and distributed energy resources. They're not distributed generation, but I consider these resources as well. And because they're inherently distributed, they always capture that locational value. On the other hand, certain technologies, particularly the two kind of shiniest ones that everybody sort of thinks about and is supporting, rooftop solar and distributed storage, that's a Tesla Powerwall there, are inherently modular. So the core technology at their base, the solar cell, the battery pack, you can deploy it anywhere from a tiny household scale to a massive solar farm or storage farm. So they're building 300 megawatt storage facilities in California right now to replace whole power plants worth of capacity. Or you could put a 13.5 kilowatt hour storage system in your garage, Tesla Powerwall. Right? So they're deployed across all of these scales. And that's important because there are real economies of scales of these technologies. Even though the core technology itself is modular, deploying 1,000 small systems is a lot more expensive per kilowatt or per kilowatt hour than deploying one very large system. And so this leads to a really important trade-off from a societal perspective between the higher locational value of distributed resources that argues for making them small and distributed, and the higher economies of scale, or the higher cost due to economies of scale for smaller systems, which argues for making them big and centralized. So you have this sort of interesting tension for those technologies. And when locational value exceeds the incremental cost due to foregone economies of scale, it makes sense to build distributed. And where that's not the case, from a societal perspective, it would make sense to build larger societal solar farms. Unfortunately, that's not a trade-off that basically any policy out there currently captures, right? So we pay the same amount in investment tax credit for solar anywhere in the country. The federal policy is just 30% of the cost of the system, regardless of where it is or how much locational value it produces. We provide the same statewide subsidy per megawatt hour in New Jersey, regardless of whether it's located on a distribution feeder that's about to get upgraded and we can avoid that cost, or if it's actually on a distribution feeder that's saturated with wind and solar and is causing upgrades because it's there. So what we need then is regulation and markets to create a level playing field for these technologies so that when you and I think about the private incentives that we face to buy a storage product or a solar product, we're internalizing all of this, these trade-offs kind of inherently, right? And that's not the case today. So one of the topics later in the class will be how do we reform regulation to create a level playing field for both distributed and centralized systems of various scales in different locations so that we get the most effective mix of those technologies available. That brings us to the final component of the class, which is the focus on electricity regulation. As we'll see in this, the course syllabus and the outline, basically we're going to spend the first quarter of the class talking about engineering topics, the next quarter of the class talking about economics and the incentives that generators and individuals face, and then the whole second half of the class talking about how each of the vertical segments of the market are regulated. And that's because, there's regulation in all economic sectors, but I would say electricity is probably the most pervasively shaped by regulation. Right, so these are all the different regulatory agencies. You're going to learn a lot about the particular one in one location in the world through your assignments. But we regulate all of these companies for two big reasons, I would argue. One is that utilities are natural monopolies. So natural monopoly is any market where there are substantial economies of scale such that having one big company is a lot cheaper than having 2 or 3 smaller companies supplying the same volume of service. And where, partly because of that, or for other reasons, there are substantial barriers to entry to compete in that market. And we recognized early on in the history of electricity that utilities had these natural monopoly characteristics, that both the networks and early on the generation itself benefited from economies of scale. And that meant that a private company that was unregulated could get a dominant position in the market and just trounce any of the competition. And so to prevent them from abusing that position, we created regulatory compacts for each of these utilities. We said, it's fine, you're going to get a natural monopoly. We're going to say you're the only utility that can generate power or sell power in a particular area. But in exchange, we're going to regulate what you can charge for electricity and what you can build. Because otherwise, you're going to be like Facebook and be an unregulated monopoly and do whatever the heck you want, right? So certain monopolies we decide are fine. The Facebook one is an open topic in Congress these days. Others we decided because they are of critical national importance, we just can't leave it to the market to let a monopoly rule, right? So as I mentioned before, of course, electricity is critical to our economic security, to our economic activities. This is the blackout of 2003, when this entire portion of the country went dark because of a cascading fault in the power system. Right, so millions of people, tens of millions of people across New York, New Jersey, the Midwest, all without power for about over 24 hours. Right? Think about the impact of Superstorm Sandy around here on power outages. I mean, we just can't let this happen, except exceedingly rare events. And so we decide we're going to create regulation to govern these utilities. Fortunately, I don't have time to go through this history of how that evolved, but you can read it all in here. So let's talk for just a minute before we run out of time. We're just about the structure of the course, which I've hinted at a few times. Okay, so again, the topics are engineering, economics, and regulation. And what I'm hopefully going to do is, by the end of it, you're going to be able to operate in here at their intersection and understand how the different factors all influence how we design, operate, build, regulate, invest in, et cetera, the electric power sector. So the structure from the course is basically like this. So the first 3 weeks, we're going to cover engineering topics like the basics of thermodynamics, how thermal power plants generate electricity, how wind, solar, and hydro generate electricity, and how the distribution and transmission networks operate. Then we're going to jump into economics, and we're going to give you sort of a basic microeconomics as applied to the power sector. And during that, we're going to play an electricity market simulation game, where you're each going to buy a portfolio of power plants at an auction and then learn how to bid them into a competitive market. Then we're going to have a midterm, which will cover the first two topics. Okay. And there'll be no final exam. There's just going to be a cumulative term paper. And then we're going to jump into regulation, which is most of the rest, except for the end, where we'll talk about things like distributed generation and kind of open topics on regulation and decarbonization and policy. And then you'll have a cumulative term paper. A note about Friday sessions. We are not using our Fridays as typical precepts. Okay, so these are not going to be a tutorial type session where we cover, what we covered in the week. There's going to be a mix of topics. So the first 5 of the sessions are going to be graduate seminars. So for those of you who are enrolled in the graduate level course, you'll be required to attend all but one of these. And we're going to read and discuss a contemporary report or paper in a bit more detail. Unfortunately, for the undergraduates, to keep that manageable, we're not going to include you in that portion of the session. So those Fridays, you get to have a free day. Your homework or do whatever else you want. The other 5 are going to be a mix of tours and guest speakers, starting with a tour of the Princeton Central Power Plant this Friday. So we're going to go see how power is generated in heat and cooling for the whole Princeton campus on Friday during the course time, and I'll send out information about that as well as an RSVP. They said it was limited to about 15 people, and the course is a lot bigger than that now, so I'll have to figure out how that works. We're going to have to go in 2 shifts or something. And then later, we're going to go to the PJM interconnection. PJM is the regional electricity market. It's the largest in the United States. Extends everywhere from Pennsylvania, Jersey, and Maryland, which is the original PJM, all the way to Illinois. And their control center, where they operate the whole regional grid, make sure the lights stay on every day, and operate all the electricity markets in the region, is down in Valley Forge, Pennsylvania, near Philly. So we'll take a field trip down there. And then we're going to have 3 different guest speakers with experience in industry and regulation. Okay. And all, these won't be required, but they're highly encouraged for both undergrads and grads to attend, and they'll be in this class. My attendance policy is as follows. For all of you in both course levels, if you want an A in this course, I expect you to show up and I expect you to do the work. And that means that, I know there are travel, challenges for all of you throughout the semester, but you have to attend no fewer than 21 of the 23 lectures. So you can miss up to 2 and still get an A in the course, and be judicious about when you do that. Of course, and this isn't a free pass to just miss 2. You should come. But if you have to, for travel reasons, that allows you to miss basically a full week if you needed to. But I want you to tell me when you're not going to be here and why. And if you have medical reasons or you're in varsity athletics, tell me in advance, and those will not be counted towards your action. For the graduate students, I expect you to come to 4 of the 5 seminars. So again, you can miss 1, so you have to be gone for a whole week for research or a conference or something. You can do that, or you can distribute it around. So in other words, don't miss more than 2 lectures. Don't miss more than 1 grad seminar if you're a grad student, if you want to get an A in the class. If you don't care about the letter grade and you're just doing it, you want to listen or you want to do it pass-fail, then attendance is up to you. You're all adults. You can decide how often you want to come versus just do the readings, etc. So that's the policy. Any questions about that? Okay. We are going to start taking attendance next week, so make sure that you are registered if you are taking the class for a grade and you want your attendance to counter this. I'll print out the list of students. And finally, just give you an assignment, an overview of the assignments. Sorry to hold you a couple minutes late. So there's slightly different weights on the assignments, but this is all in the syllabus. There's a set of different recurring assignments. The first of which will be short answer, kind of both qualitative and quantitative assignments. And then I'm going to ask you all to formulate 3 true-false questions based on the readings. So I'm not going to give you the true-false questions. You're going to give them to me. So you're going to do the readings. You're going to identify 3 topics that you think covered critical concepts that you learned in the reading. And you're going to write a true-false question that might test somebody else's knowledge of the reading. And then of those, we're going to pick, say, 5 of them that you all submit, and we'll discuss them in class. So you get a little extra bonus points, extra credit on the assignment if we pick one of your submissions as the ones to discuss. Then alternating weeks, we're going to do this regional electricity sector assignment where you're going to pick 1 location in the world, and you're going to learn how that power sector is uniquely structured and regulated, and what the policies governing that location are. So as we go through the class topics, you're going to be thinking about, we'll learn about the general concepts, and then you're going to pick a location and dive in depth onto that specific location and how it works. So your first assignment is actually online now and is due tomorrow at 8 p.m. All of the assignments will be due by 8 p.m. on the date that they're due. And it's just short. It's only one paragraph. You need to pick a location in the world that you want to study this semester and tell me why. There's a list on the assignment of places we recommend. If you want to pick somewhere that's not on that list, you have to discuss it with us first, and we can discuss whether it makes sense for you to do that. Don't pick small, tiny island countries. Like, we want you to pick like a big market that has some interesting interactions. And throughout the course, you're going to cumulatively research how that sector is structured and regulated, and you're going to produce concise summary reports on each of those that we're going to upload to a course WordPress blog. These are the topics. And then finally, at the end, your challenge for the term paper is to take what you learned about that location, concepts you learned in the course, and diagnose several shortcomings in the current regulatory and policy environment and how you might fix those, or improve those, in order to facilitate decarbonization of the power sector and the integration of distributed resources in an environmentally friendly, reliable, and cost-effective way. You'll learn those are our goals as regulators. So I've held you too late, so I'll let you go. I'll be around to answer questions for the next little while, and I really appreciate you coming. Thank you. If you're not registered yet for the course and you need to register, please do so quickly. If you're a graduate student and you're in the 400 level course, please register for the 500 level course. Switch over. And if that hits the 15-person cap for some reason, let me know. Good. Thank you. Okay. Are you able to watch one of those on the recording? Oh, yeah. Okay. Do that. Yeah. Okay. I can look for that one. No, as long as you we have an agreement, you're going to watch the lectures and. I just turned this up.